Hello students, welcome to JCE Connect. So in previous lectures we have solved some numerical problems on Pelton wheel where we have calculated work done by the jet and efficiency of the jet. In this particular session, so I'll be solving a problem that is a design of a Pelton wheel, how to design a Pelton wheel and working proportions of a Pelton wheel. So let us first discuss about the design procedure of a Pelton wheel. So what do you mean by design of a Pelton wheel? Here the design of Pelton wheel means, the following data is to be determined. So here the design means not we're completely designing the buckets or completely designing the runner of a Pelton wheel. So just we are calculating here the working proportions of a Pelton wheel. So in this particular design, so the design means we need to calculate the diameter of the jet, then we need to calculate the diameter of the wheel, then the width of the bucket, so which is to be generally taken, the value is between 3 times of diameter of jet to 5 times of diameter of jet. So I am taking here as 4 times of diameter of jet. Then you have to calculate the depth of the bucket, which is to be taken 1.2 times of diameter of jet, and number of buckets on the wheel. The number of bucket on a wheel means this is the wheel. This is the wheel. How many number of buckets to be? Optimum number of buckets we need to calculate. Optimum number of buckets. So the jet, whatever it is striking, it should not miss by striking the bucket. Okay. Then size of the bucket means the width and depth of buckets are to be calculated. Okay. So all the dimensions are being proportioning by using the diameter of jet here. Okay. So this is a design of a Pelton wheel. Then design procedure. So if you look at the design procedure, so in design procedure the power will be given, how much power Pelton wheel to be designed, or how much power needs to be developed by the Pelton wheel, and the RPM also given. For the given power and for the given RPM, you need to design the Pelton wheel. So design a Pelton wheel means, as I discussed previously, so that parameter needs to be calculated. So in this particular design procedure, the design of a Pelton wheel turbine to develop a known power, P running at n RPM with an overall efficiency of eta O, the following procedure is adopted. It means the power will be given, RPM, that is RPM of that wheel will be given, then how much efficiency it needs to generate, that is overall efficiency. Then for that you need to calculate what the diameter of jet should be required, or how many number of jets are required to develop a particular power, or what diameter of wheel is required, and how many number of that is optimum number of buckets are required to generate the given power. So for that, so as we know the overall efficiency formula, so that is the first step we need to calculate, find the rate of flow through the turbine. So since the overall efficiency will be given, the shaft power, the known overall efficiency and the known shaft power, then we can easily get the how much discharge is passing through the turbine. So overall efficiency, as we know, it is the ratio between the shaft power and the water power. So shaft power is a P, then the water power is rho into G into H into Q. So in this the P is given and the head will be given, then you need to calculate how much discharge is passing through the turbine, that is Q. So that is eta O, that is P divided by rho G into Q into H. So from this you can easily get the value of Q. So this gives you the discharge through the turbine, total discharge. Then from a known head H is given, compute the jet velocity. So as we know the formula for calculation of actual velocity, that is V equal to CV into root of 2gh. Since H is given here and CV will be given, if not given, CV to be assumed between 0.97 to 0.99, and bucket velocity as that is a U, or you can call it as a wheel velocity, that can be easily calculated, that Ku times of root of 2gh. So here this root 2gh, U equal to Ku into, actually this is theoretical velocity. As you know, the Ku is the speed ratio. The speed ratio is what? It is a ratio between the wheel velocity and the jet velocity. Wheel velocity and the jet velocity. From the speed ratio we can easily get the wheel velocity or the bucket velocity, that is U equal to Ku into root of 2gh. And this Ku to be assumed or between 0.462, as we know the value of Ku is generally lying between 0.43 to 0.47 or 0.48, and theoretically its value is 0.5, but that 0.5 is not actually possible. Some practical problems, so we need to take between 0.43 to 0.47. So once we calculate the velocity of the bucket or velocity of the wheel, the next we need to calculate, so what is the pitch circle diameter or diameter of wheel. So that diameter of the wheel, for wheel diameter it is also called as a pitch circle diameter. So as we know the formula U equal to pi dn by 60, this is rotational velocity. The rotational velocity U equal to pi dn by 60. Since n is known and U is known, you can easily get the diameter of wheel, that is d equal to 60 into U divided by pi n. Then after calculating the diameter of the wheel, calculate the diap jet. The diap jet to be calculated by using the formula, that is a ratio between, pitch circle diameter to jet ratio. So as we know the jet ratio will be d by d, that is a diap wheel divided by diap jet gives you the jet ratio. From this we can easily get the diameter of jet. If we know the this jet ratio, generally for a maximum efficiency, this ratio will be between 11 to 14. Then after this one, fifth step, obtain the total jet area. The total jet area can be given as A equal to Q, because we know the total discharge divided by the velocity. This is the total area of jet. Then also you can easily get, once you get the total area of the jet, if number of jets are n number of jets are provided, then area of single jet can be calculated A equal to pi by 4 into d square. Okay, A equal to pi by 4 into d square. This is the total area of jet. This is area of single jet. Okay, then find the number of jets. Then calculate the number of buckets required, optimum number of buckets on the wheel. That can be calculated by using the formula Z equal to 0.5 times the jet ratio plus 15, where m is d by d, diap wheel divided by diap jet. So after calculating the number of buckets, then you have to find the dimensions of the bucket. The dimensions of bucket means, as we know that this is the shape of the bucket, This is the shape of the bucket. So we need to calculate what is the width of the bucket, what is the groove size, then what is the radial length, then the depth of the bucket. So how much to be taken, this B, L or C, as I discussed previously. So you have to express these things in terms of diameter of jet. I hope you understood this one. This is what we call as a design of a Pelton wheel. Okay. So next we'll take one numerical problem and we'll try to understand whatever the procedure we have been discussed so far. So you can easily understand the procedure what I have discussed if we solve one numerical problem. Okay. So try to understand this design procedure. This is the design of Pelton wheel is very important for the examination point of view. Many a times the question will be asked in a VTO question paper. So generally it is been asked for 12 to 15 marks. Sometimes for 20 marks also it is been asked. Design a Pelton wheel for the given data. So like that the question will be asked. So we'll see how to design a Pelton wheel. Solve one design problem so we can understand the procedure of Pelton wheel design. So as we discussed in previous lectures, the design of Pelton wheel means the following data is to be determined. So that is, you have to determine the diameter of the jet, then the diameter of the wheel, capital D, then the width of the buckets, which is given by 4 to 5 times of diameter of jet, depth of the bucket, which is given by 1.2 times of diameter of jet, then the number of buckets on a wheel, it will be given as Z equal to D divided by 2 into D. This ratio D by D is nothing but a jet ratio, plus 15. Then the size of the bucket means the width and depth of the buckets are to be calculated. Then let us take one design problem, that is design a Pelton wheel. Our Pelton wheel is to be designed for a head of 60 meter when running at 200 rpm. The Pelton wheel develops 95.6475 kilowatt shaft power. Then the velocity of the bucket 0.45 times the velocity of the jet. Take the overall efficiency as 0.85 and take CV value as 0.98. So these are the datas given. So let us first write the given datas. So the datas given here are the head available to supply water into the turbine, that is 60 meter, and the speed of the wheel or a rotor as a 200 rpm, it is given. So we have to maintain this much of a power, this much of a speed. Then the shaft power to be generated as 95.6475 kilowatt. Then the velocity of the bucket to be taken 0.45 times the velocity of the jet. Then the whatever the Pelton wheel we design, that should give overall efficiency of 85%. Means after considering all the losses, finally it should give 85% efficiency at least. Then the CV value should be 0.98. So for these given datas, we need to design the Pelton wheel. So the design of Pelton wheel means, as I discussed previously, that is the design of Pelton wheel means to find the diameter of the jet D, then the diameter of the wheel D, capital D, then the width and depth of the buckets and the number of buckets required, that is optimum number of buckets required on the wheel. That is the design of Pelton wheel. So to calculate these things, let us first calculate what is the velocity of the jet and diameter of the wheel, capital D. Calculate the velocity of the jet. The velocity of the jet can be calculated, that is actual velocity of the jet, CV into root of 2gh. So in this we know the value of CV and we know the capital H. Substitute the values here. G is acceleration due to gravity. Then we get the velocity of the jet as 33.62 meter per second. Then once we know the velocity of the jet, then the bucket velocity can be easily calculated, because the bucket velocity they are mentioned in the problem, that should be taken 0.45 times the velocity of the jet. 0.45 times the velocity of the jet. That is u equal to u1 equal to u2, that is 0.45 into v1, that is 0.45 into 33.62. So which gives the bucket velocity as 15.13 meter per second. But as we know the peripheral velocity, this u is peripheral velocity that can be given as pi dn by 60. This u is because the rotor will be like this. These are the buckets. So then the bucket initially takes the motion, linear motion, then it starts rotating. Then this rotational velocity can be given as 5 dn by 60. From this, because we know the value of u, we know the value of n, the d can be easily calculated. That is whatever the what is the diameter of wheel required. So the diameter of wheel required will be 1.44 meter. Okay. Then so the diameter of jet can be calculated easily. To calculate the diameter of the jet, we need to calculate first what is the discharge, total discharge. To calculate the diameter of jet, the overall efficiency formula, as we know, the shaft power by water power. Shaft power, that is the power at shaft divided by water power, that is W into Q into H, where W is the specific weight of the water, Q is the discharge, and H is the head. So in this, the power is given, specific weight, that is 9.81, and Q is the unknown, and H is given. So from this we can easily get the value of Q. So value of Q we have obtained as 0.1912 meter cube per second. I hope you understood this one. So you have to remember this overall efficiency formula, that is shaft power by water power. Shaft power by water power. So from this we can get Q, value of Q. So once we get the value of Q, then next it is the next you have to calculate the discharge Q. Q, we know the formula Q equal to area of jet into velocity of jet. The area of jet can be given as pi by 4 into d square into v1. Substitute value of Q here, we get the diameter of jet as 0.085 meter, 85 millimeter. Then the size of the buckets, that is means the width of the bucket to be calculated, and the depth of the bucket also to be calculated. That is, this is the plan of the bucket. So we need to calculate this width of the bucket. We also calculate the groove width, and the radial distance can also be calculated, and also the depth of the bucket, that is this depth. Sorry, the depth is this one. The depth of the bucket to be calculated, C. So width of the bucket to be considered here is 5 times of D, or you can consider 4 times of D. That is, it is generally varying between 4 to 5 times of diameter of jet. Then we get as a 425 millimeter. Depth of the bucket is 1.2 times depth of diameter of the jet. Then we get as 102 millimeter. Even you can also calculate the groove width. That groove width can be taken as a 0.8 times of D, generally 0.8, and that also can be calculated. But if we calculate the width and depth, that is sufficient for the design of a Pelton wheel. then the number of buckets on the wheel can be calculated by using the formula. So that is Z equal to D by D, that is this one. This will be actually 0.5 times of M plus 15, where M is the jet ratio. Okay, then substitute the values here. We get the optimum number of buckets required. The optimum number of buckets required are 24 numbers. Optimum number of buckets required is 24 numbers. I hope you understood this design. Let us take one more problem. That is the problem given here as the following data relate to a Pelton wheel. The head given is a 72 meter. The speed of the wheel is 240 rpm. Shaft power of the wheel is 115 kilowatt. Speed ratio 0.45. Coefficient of velocity is 0.98. Then the overall efficiency 85%. Design the Pelton wheel. So many times in exam the problem will be given like this. The following data is related to Pelton wheel. So the data will be given like this, and they'll ask you to design the Pelton wheel. As I discussed previously, the design of Pelton wheel means you have to calculate the diameter of the jet, diameter of the wheel, the number of buckets required, how many number of jets are striking, and the power that is the shaft power will be given, then the RPM will be given, everything will be given. So for that you need to design the Pelton wheel. Okay, so here let us write first the given data. That is head available at inlet of the turbine is 72 meter. Then the RPM of the wheel is 240 RPM. Then the power, that is shaft power, of considering the overall all the losses. Finally the power reaching at shaft will be 115 kilowatt, or it is generating 115 kilowatt. Then the speed ratio will be 0.45, the CV is 0.98, and the overall efficiency is 85% to be achieved. So for that, so let us calculate first the diameter of the wheel. So the diameter of wheel is capital D is 60 into U divided by pi n. But where the U is what? The rotational velocity or peripheral velocity, Ku into root of 2gh. So this is we know this formula very well. So use this formula. Ku is the speed ratio which will be given. If not given, you have to assume this one. Generally it will be given, and if not given, it is to be assumed between 0.43 to 0.48. Then U we get. Then substitute here, we get the diameter of the wheel. Then calculate the diameter of the jet, because we know the overall efficiency formula, shaft power by water power. So this is nothing but shaft power divided by water power. Shaft power is given 115 kilowatt. Substitute the value of W here, and the U, Q is unknown, H is known. Then calculate Q. This much is the discharge coming. And then we know Q equal to A into V1. Substitute A is pi by 4 d square, CV root of 2gh. Then from this we get the diameter of the jet. Then once we get the diameter of the jet, then the size of the buckets can be easily calculated. So size of the bucket means, as I said, that this is the bucket. We need to calculate the width of the bucket, then the groove length or radial length. The width of the bucket will be the 4 to 5 times of d. And the length, the radial length will be 2.4 to 3.2 times of d, and groove length will be 1.1 to 1.25 times of d. And depth of the bucket can also be calculated, that is 1.2 times of d. Then calculate the size of the bucket. The size of the bucket will be generally taken 5 times of d. Then substitute the value of d here, that is diameter of jet, we get as a 407 millimeter. The radial length of the bucket L can also be calculated 2 to 3 times of d. Let us take 2.5 times of d. Then we get as a 3.5 millimeter radial length of the bucket. Then the depth of the bucket can be generally taken, that is between 0.8 to 1.2 times of d. Let us take 1.2 times of d. We get as a 97.68 millimeter. Then the number of buckets on the wheel. So this is the formula to be used. The optimum, we get the optimum number of buckets on a wheel, that is d divided by 2d plus 15. We know the capital D, we know the small d. Substitute here, we get the optimum number of buckets as 24 numbers. So optimum number of bucket means this is the wheel. So the number of buckets required on this wheel. So we can generate the power whatever mentioned. So that much of power can be easily generated. These are called optimum number of buckets. So okay, so 24 number of buckets we required. So I hope you understood this problem. So like this you have to design the Pelton wheel. So design up, I'll repeat once again, the design of Pelton wheel means, so calculating the diameter of the jet, calculating the diameter of wheel, then the number of jets to be calculated, then the number of buckets to be calculated. So if we calculate these all parameters, so we can say it's a design of Pelton wheel. Okay, so this kind of problem generally will be asked for 15 to 20 marks. So you can easily get 15 to 20 marks so in this problem. Okay, thank you.